Ok, adesso stiamo registrando. Okay, do you see the slide?
Yes.
Okay, so we can start. So as I anticipated yesterday, in the first part of today's lesson, we will solve some problems about the discrete symmetries that we studied yesterday in the previous lesson, and then we will move on to the Hadron chapter. So let's start with problem 1. So using J omega PC equal 1 minus minus, check the conservation of parity and charge conjugation in the decay omega into pi plus pi minus. So this JPC is the standard way to provide, the standard notation to provide the quantum numbers, the relevant quantum numbers. So J is the total angular momentum, and then P and C are the essentially the eigenvalue of the parity and charge conjugation operator. Okay. So we have all the information on the initial state, and we want to check that also that parity and charge conjugation are conserved in this specific decay of the omega of the omega meson. So we'll move now to the board. Se avete le slide, il PDF che ho messo ieri, vi conviene tenerlo aperto così avete il testo dei problemi a disposizione. Che adesso con la lavagna ovviamente dovrò nasconderlo.
Non ho visto quegli slide su Google Classroom, dove sono?
So these are the slides that I put, so these are yesterday's slides, not today's slides. So lesson 9. They should be at the end of lesson 9.
Yes, Professor, when you updated the slides, actually the new version didn't have the exercises at the end.
Okay. Sorry for that. Okay.
It's not problem. I think I can. I will try, Benjamin. I will try to upload it on Classroom, and if I can, the professor can.
Okay, I will update the lesson 9 with the full version, including the problem. So sorry, it was my mistake then. Okay.
No, sorry, thanks. I didn't know if I just missed something anyways.
Thanks for noticing me. Yeah. Okay, my mistake. So let's move on now on the board. Okay, you now see the board, right?
Yes.
Yes.
Okay, so this is problem 4.1. Let me write it here. Okay, so I will just read the text and then I will proceed with the solution. So using J omega PC equal 1 minus minus, check the conservation of parity and charge conjugation in the decay omega into pi plus pi minus decay. So from the information that we have in the text, the initial state angular momentum Ji, that is the angular momentum of the omega meson, is 1. Okay, because we know from the text that J omega PC is 1 minus minus. And so by angular momentum conservation, we have to require, of course, that the angular momentum in the final state must also be equal to 1. So we have to require that the Jf, which is the J of the final state pion pair, which is in general the sum of the orbital angular momentum plus the spin, okay, this must be 1 to enforce angular momentum conservation in the decay, okay? Now, yesterday we anticipated that the pions are pseudo-scalar mesons, so they have the spin 0. This we will study even more better today. So for sure, the spin of this pion system is 0. And so what we learn by applying the angular momentum conservation is that the orbital angular momentum of the final state must be equal to 1. Okay. Now, what about parity? So the parity in the initial state is the parity of the omega meson, which is -1, and this we know from this from the information on the text. Okay. What about then the parity in the final state? So the parity in the final state is the parity of the pion-pion system, and as you know, this is given by -1 to the L pi pi times the product of the intrinsic parities of the two pions. Okay, so this is -1 L pi pi, and the intrinsic parity of the pions is -1, as we know, because they are pseudo-scalar mesons. So this is -1 times -1. Okay, so overall, this is, of course, a +1. So overall, we have -1 to the L, which is 1, as we know from angular momentum conservation. Okay, and so overall, this is -1, and it is indeed equal to the initial parity. So parity is conserved in the decay. What about now charge conjugation? The initial state charge conjugation is the charge conjugation of the omega meson, which is -1, as we know from the text. And then for the final state, we have C pi pi, that is -1 L pi pi, because again, the pions are scalar objects, so they don't have a spin component. And so this is just -1 to 1, so this is again -1, and again, this corresponds to the charge conjugation of the initial state. So both parity and charge conjugation are indeed conserved in this decay. Okay, pretty simple. Let me now move on to the slide, to the second problem. Okay, problem 2. So the psi prime meson is an 2 S31 CC bar state. Calculate its JPC quantum number. So what you see here is the standard spectroscopic notation. So essentially here we have all the information about the angular momentum, the spin, and the total angular momentum. So the psi prime, as we will study next in the course, is indeed an excited state of a CC bar bound state. Okay, it is one of the state of the charmonium. So we have now, based on this information, to calculate the JPC quantum number of this meson. So we switch back to Word. All right. So this is problem 4.2. So from the text, we know that the quantum numbers of these psi prime mesons are 2 S3 1. Okay, and this corresponds to the standard spectroscopic notation. So this is the principal quantum number. Then we have the angular momentum. Then we have J, and then we have 2s plus 1. The same notation that you use also in atomic physics. Okay. So here we have a lot of information indeed. Okay. So from the fact that it is an S wave, this corresponds to an L equals 0. Okay. Then, since 2s plus 1 is equal to 3, this must be S must be equal to 1, and J is, of course, 1. So now let's calculate the quantum numbers. So the parity of the psi prime, it is -1 of the relative orbital angular momentum of the CC bar pair times the intrinsic parity of the charm quark and the charm antiquark. So here we have -1 L psi prime, and then we have the intrinsic parities, which are positive for the quark and negative for the antiquark, as we studied yesterday. Okay. Now, from the information on the angular momenta, we know that the orbital angular momentum of the psi is 0. So this is -1 to the 0 times -1. So overall, this is -1. let us now consider the charge conjugation. So in this case, the charge conjugation of the psi corresponds to the charge conjugation of a system of fermion pairs. Okay, the C and the C bar works. So this affects not only the spatial component of the wave function, but also the spin component of the wave function, as we have seen yesterday. So overall, this is given by -1 to the L C C bar plus S, which is the spin C C bar. That is -1 to L psi prime plus LS psi prime. And we have all the information in hand. So this is -1, then it is 0 for the orbital angular momentum, and 1 for the spin. So this is also -1. And so now we are done, because we know the angular momentum, the total angular momentum, we know the parity and charge conjugation eigenvalue. So we can say that the JPC of the psi prime meson is 1 minus minus. All right. Okay, let's move on to the next one. If you have doubts or problems, just interrupt me as usual. So problem 3. Find the possible values of JPC for a spin 1/2 particle and its antiparticle if they are in an S wave or in a P wave state. So, back here. All right. So in this case, we have a system of a fermion and an antifermion, okay? And as you know, and as we've already studied before, the total spin of this system can be either S equals 0 or S equal 1, okay? So, so this is problem 4.3, okay? So we have two possibilities for the spin couplings. So either S equals 0, which is a singlet state, or S equal 1, which is a triplet state. Okay. Now, let's consider the first part of the problem, so where these two fermion antifermions are in an S wave. So S wave means that the orbital angular momentum is 0, as you know. So we can calculate the total angular momentum, which is L plus S. And here we have indeed two possibilities. So this is 0 if the spin is 0. And in this case, the spectroscopic notation, so the 2s plus 1 will be S0, 1. Or it could be 1 if the spin is 1, so in the triplet case. And in this case, the quantum numbers of this state are S3, 1, where capital S, as usual, denotes the S wave, so L equals 0. So let's calculate now the parity and the charge conjugation. So the parity for this fermion antifermion system is, as usual, -1 to the L, and then the intrinsic parity of the fermion and the intrinsic parity of the antifermion. So we are in an S wave, so L is equal to 0, so we have -1 to the 0, and then the intrinsic parity of a fermion, which is +1, and of the antifermion, which is opposite, -1. And so overall, this is -1. So this depends only on the value of L, which is 0. Now, let's now calculate the charge conjugation. for these two states. So let me start with S10, because in this case, we have to take into account also the spin component of the wave function. Okay, and so if you remember from our 2 lessons ago, this is -1 L plus S for a fermion-antifermion system. So we can substitute. This is -1. Then we have 0 for L and also 0 for S in this specific case. So this is +1. Let's now consider the other state. So the 3S1 is always -1 L plus S. So this is -1, but now L is equal always 0 because we are in an S wave, but now the spin is 1. So this is -1. And so we can draw the result for this first part of the problem, that the JPC for the state S10 must be 0 minus plus. And the JPC for the state S31 must be 1 minus minus. Tutto chiaro, ragazzi? Is all clear? Mi sentite? Mi date un cenno, per favore?
Sì, prof.
Ok. Ok.
Puoi rispiegare la notazione, scusi?
Come scusa?
Se puoi rispiegare la notazione, quel 1 meno meno,
Sì,
per
sì,
cosa
sì.
sta?
Allora, the notation is given here. So 1 is the value of J, the total angular momentum, which is given here for this case. So it is 1 in this case and 0 in this other case. And then these minus minus are the corresponding value of the parity and charge conjugation eigenvalues, the one that we calculated here. So it is minus for the parity, so odd parity in both cases, minus and minus. And we have a plus charge conjugation here and a minus charge conjugation there.
Okay, thank you.
Chiaro? Okay.
Yes.
Okay, so let's now solve the second part of the problem. So the second part is essentially the same, but now with the fermion and antifermion in a P wave. So let me take a new page. So this is part B. So now we are in a P wave. And so this corresponds to L equal 1. And so as before, we calculate the total angular momentum as L plus S. And so we have to check here all the possibilities. So this is going to be 1 in the case of a singlet spin state, okay, S equals 0. And so in this case, our quantum numbers are P1, 1. Okay, P corresponds to L equal 1. Or if S is equal 1, we have now to add the angular momenta, the spin and orbital angular momentum. And as you know, in quantum mechanics, we have now 3 possibilities, 0, 1, and 2. And so in this case, our quantum numbers will be given by P3, 0, P3, 1, and P3, 2. Okay, so the spin is 0, but now we are adding with the orbital angular momentum, which is non-zero, it is 1. So we have 3 possible values for the total angular momentum. And so we have to treat them all separately. Let's start for the parity. So the parity of this fermion-antifermion system is given as usual by -1 to the L. Then we have intrinsic parity of the fermion and the antifermion. So L is equal to 1 in this case. So this is -1 to 1. +1 -1 for the intrinsic parities, and this is overall +1. Let's now calculate the charge conjugation, and here we have to distinguish between the various cases. So F bar for the 1p1 case, this is -1 L plus S, as we have seen also before. So we just need to substitute -1, then we have 1 for the orbital angular momentum, and 0 for the spin, because this is the singlet case, and so this is just -1. What about the others? Well, the only thing that matters here is the sum of L plus S, okay? Which is the same for all the three other cases. So we can group all them together. So the C of the P30 will be equal to the C F bar for the 3P1, which is also equal to the C F bar for the 3P2, which is -1 to the L plus S, because both L and S are common to all these three cases. So for all of them, this is -1, and we have 1 plus 1. So overall, +1. And so we can now draw our results. So the JPC for the 1p1 state will be 1 plus minus. And then we have the JPC for the 3p0 state will be a 0 plus plus. The JPC for the 3p1 state will be a 1 plus plus. And finally, the JPC for the 3p2 state will be 2 plus plus, where 0, 1, and 2 are the three possible values of the total angular momentum. And parity and charge conjugation are all positive for all of them. So even. Okay. Okay, let's move on to the next one. Problem 4. So calculate the quantum numbers of parity and charge conjugation of the following neutral mesons. The ρ0, so the quantity in parentheses is the mass of these two mesons in mega electron volt in MeV. Okay, so the ρ0, which has a total angular momentum of 1 and a decay width of 149 MeV, and the F20, which is a bit heavier. It is an excited state, so it goes with a quantum J equal 2 and with this decay width, both decaying into a pi plus pi minus pair. So let's move on there. Okay. So, so this is problem 4 by 4.4. Okay. So in this case, the text provides us the decay width. Okay. So if you remember, the meaning of this is that for certain hadrons, okay, the decay time is so short that cannot be measured experimentally, but what we can measure is instead a related quantity, which is the decay width of the resonance. Okay, that is the width at half maximum, if you remember. This we already mentioned, but we will come back to this several times during the course. Okay, and by the uncertainty principle, if you remember, we made the following argument in one of the first lessons. So we know that delta E times delta t by the uncertainty principle is h bar square, divided by 2, sorry. By delta e, we can take half of this gamma, okay? So the half of this full width at half maximum. So we take gamma half. By the time we take the decay time, and this is still order of h bar divided by 2. And so we multiply by 2 and we get that gamma times tau is of the order of h bar. And so we can invert this and obtain the decay time, in this case for the raw meson, for our case, which is h bar divided by gamma. We know gamma, and we have to calculate the decay time. So what we do here is to multiply on the numerator and denominator by the speed of light, c. And the reasons for that is that, as I probably mentioned in the very, very first lesson, this quantity h bar c has a known value. So it is approximately, let me put here, approximately equal to 200 MeV per Fermi. Okay, so it is also easy to remember. And then in the denominator, we have the decay width of the rho, so which is provided by the text, so 149 MeV, times the speed of light that we, of course, have to express in terms of Fermi per second. So it is 3 × 10⁻23 Fermi per seconds. And once you do this calculation, you obtain something like 4.4 10⁻24 seconds. So now the question for you. Given this decay time, what is the fundamental interaction that regulates this decay? It is strong, it is electromagnetic, or it is weak? Can you tell me?
Strong?
Yes, it must be strong, because only strong decays can have such an extremely short decay time. Okay, so it is a strong process. And as we have seen yesterday, this implies that both P and C must be conserved in the decay. Okay, because only weak interaction does not conserve parity and charge conjugation. So both P and C must be conserved in the decay of the rho zero into a pi plus pi minus pair. And so we will make use of this, of course. Now, what we know from the data? From the data, if you remember, we know from the text, we know that the angular momentum of the rho is 1. So the J rho zero is 1. And so we enforce angular momentum conservation. So this must also be the same for the final state, so for the pion pairs, which is in general L pi pi plus S pi pi. This must be equal to 1, okay, to ensure angular momentum conservation. Then again, we know that pions are pseudoscalar objects, so they have zero spin. So this implies that the angular momentum of the pion pair must be 1. And so we are in a P wave. Okay, now we have everything to calculate the quantum numbers. So the parity of the rho zero must correspond to the parity of the final state, because parity is conserved in this strong decay. Okay, so we enforce this equality. And this we know how to calculate, because this is -1 L pi pi times the product of the intrinsic parities of the two pions, pi plus and pi minus. So this is -1 to the 1. The intrinsic parities is negative because pions are pseudoscalars. And so overall, this is -1. What about charge conjugation? 0, 0. This, again, it must be conserved in the decay because it is a strong decay. So this must be equal to the charge conjugation of the pion-pion system. Since pions have spin 0, the only term that matters is the one related to the spatial component of the wave function. So we don't have spin component here. And so this is simply -1 to 1, so -1. And so we can write down our result that the JPC for the row 0 meson is 1, because the J is 1, okay, and then minus minus. Okay, this was the first part, okay, for the first meson. Let's now work out the other meson, so the F20 meson.
Sorry, just a question, if I may interrupt you.
Sure, go ahead.
Okay, sorry. So you said because it's L pi pi equals 1, it's a P wave, but where did we use it afterwards?
The P wave, P wave means L pi pi equal 1, and we use it here and here.
Okay.
So 1 here and 1 here. Okay, so let me take a new page. And let's work out now the second case. So the second case, let me remind you from the text, it is the F20 1270 meson with the J equal 2 and with the decay width of 185 MeV. Okay. So let's calculate also in this case the decay time. So the tau F20 is h bar c divided by gamma c. So this is approximately 200 MeV dot Fermi and 185 MeV times the speed of light, 310 to the 23 Fermi per second. And so the value that you obtain here is 3.5 10 to the minus 24 second. So this is clearly, again, a strong decay. And so again, we must enforce parity and charge conjugation conservation, in addition to orbital angle, to angular momentum conservation. So in the initial state, the angular momentum is 2, as we know from the text. So it must be 2 also in the final state, so in the pi pi state, which is L pi pi plus S pi pi. Again, the spin are 0. And so we learn here that the orbital angular momentum in this case must be equal to 2. And so we now just repeat the exercise. So for the parity, this must be equal to the parity of the final state, because parity is conserved. And so this is -1, L pi pi, intrinsic parities both negative. And so this is -1 to the second, because L is equal to 2. And so in this case, it is positive. And similarly, for the charge conjugation, we have that this must be equal to the charge conjugation of the final state. So this is -1, L pi pi. We don't have a spin component in this case because we are talking about pions. And so this is -1 to the second. And so this is +1. And so in this case, the result is JPC of the F20 equal to 2 plus plus. All right. Now, if there are no questions, let's move on to the next one. Problem 5. So calculate the value of Cp for a system of 2 neutral pions in an S wave, or for a system of 3 neutral pions, where Cp means essentially consequent application of the charge conjugation and parity operator together. So essentially the product of the two quantum numbers. So let's move on to the blackboard. Okay. So this is problem 4.5. So the first case is calculating CP for a system of two neutral pions in an S wave. So it's a system of let's say, a pi 0 in an S wave. So S wave means that the orbital angular momentum of the system must be equal to 0. Okay. Now, if you remember, the pi 0 is one of those cases of neutral particle which coincides with its own antiparticle, and so it is an eigenstate of the charge conjugation. So we know that, as we have seen yesterday, that C over the pi 0 state give us again the pi 0 state with eigenvalue plus 1. Okay, this we have seen yesterday at lesson. So now we have a system of two pions, and charge conjugation is a multiplicative quantum number. So the charge conjugation for the system of the two neutral pions is just the product of the two eigenvalues. That is plus 1 times plus 1, that is plus 1. What about parity? Same story. This is minus 1 to the L pi pi times parity, intrinsic parity of the two pi zeros, which are both negative. So this is minus 1 to the 0 because we are in an S wave, and then we have minus 1 times minus 1. So overall, this is plus 1. And so we can already provide the results that the CP of the pi 0 system is plus 1 times plus 1, and so it is plus 1. Let's now consider the other case. So in this case, we want to calculate CP for a system of three neutral pions. So pi 0, pi 0, pi 0. Okay. So for the charge conjugation, nothing changes. Okay, we have just to multiply 3 times plus 1. So the charge conjugation of these three pion system is just the product of the three eigenvalues. So this is plus 1 to the third, that is plus 1. The parity is a bit more tricky, okay, because now we have a system of three particles, if you remember. So suppose we have a pi 0 here, a pi 0 here, and another pi 0 there. Okay. So we have the L12, which is the relative orbital angular momentum of the first pair, and then L3, which is the one of the third pion with respect to the center of mass of the other two. Okay, as we saw yesterday for a system of three particles. So for the parity of these pi 0, pi 0, pi 0, we have minus 1 to the L12 plus L3 in general, and then we have the intrinsic parities of the three pi zeros. So this is minus 1 to the L12 plus L3 times minus 1 the cube, that we can express as minus 1 to L12 plus L3 plus 1, where this additional 1 in the exponential takes into account the minus 1 from the intrinsic parities. Now, let's now compute the product. So the CP for these three neutral pion system. So the C is +1, as we calculated, and the parity, we still have an ambiguity. So it is L12 plus L3 plus 1. Okay, so in this case, the value of C is irrelevant. So this is just given by -1 L12 plus L3 plus 1. And so we have two possibilities. So this is going to be equal to +1 if L12 plus L3 is an odd number, or -1 if L12 plus L3 is an even number. So a question for you. So what can we exploit in order to solve this ambiguity? Try to think a little bit. So which condition we can or we must impose in order to solve this ambiguity? So we have a system of 3 pi zeros. Non vi dice niente questo? No idea? Okay, I'll tell you. So the condition that we have to impose now in order to solve the ambiguity is that we are dealing with a system of undistinguishable bosons, right? 3 pi zeros. And so the total wave function must be symmetric under exchange of any of those. So the condition that we have to impose here is the symmetry of the wave function for identical bosons. And so if you remember now from a couple of lessons ago, the symmetry of the wave function in general is given by the symmetry of the spatial component, that is our usual L dot, -1 to the L dot, times the symmetry of the spin component S dot. So for the total angular momentum, we still have the ambiguity. So -1 L12 plus L3. For the spin, we know that this is 0. Okay. And since we want our total wave function to be symmetric, this equality must be equal to +1. Okay. And so this is only possible if L12 plus L3 is an even number. And so the correct assignment is Cp of the 3 pi zeros must be -1. So here we are imposing that the wave function is symmetric. Chiaro ragazzi? Datemi un cenno.
Yes.
Sì, sì, proprio.
Ok. Quindi in questo caso, so in this case, the text didn't provide the value of total L because we could derive it by applying the symmetry of the total wave function. Now, a couple of more problems. So problem 6. The pseudoscalar meson eta 0 has quantum numbers JPC equals 0 minus plus, and the full width at half maximum 1.3 keV. Determine its lifetime and which fundamental interaction induced the decay, and say if the following decays are allowed or forbidden by the conservation laws. So we go back here. Okay. So problem 4.6. So let's start again in the usual way. So we know that the decay time is h bar over gamma. So this is h bar c over gamma c. And so this is approximately equal to 200 MeV times Fermi. And now we have a width of 1.3 keV. So 1.3 10 to the minus 3 MeV times 3 10 to the 23 Fermi per second. So the decay width is, in this case, much thinner, okay, much tighter than for the previous case. And in fact, what you obtain here is something like 5 10 to the minus 19 seconds. So based on this, can you tell me which kind of interaction induced this decay?
Should be weak.
No, it's too fast to be weak.
Electromagnetic for this one, no?
Yes, it is electromagnetic, okay? So it is an example of an intermediate case where it is too slow for being strong and too fast to be weak. So it is a clear example of an electromagnetic decay. And as we've seen yesterday, parity and charge conjugation must be conserved in all electromagnetic processes. So again, we have to enforce that P and C are conserved in the decay. Okay, so C and P must be conserved, and it is an electromagnetic decay. So let's move on to, so this was the first part. Let's move on to the second part. So in the second part, the requirement was to check if the decay of eta 0 into 2 pions or 3 pions are allowed or forbidden by the conservation law. So let's start with the first case. So eta 0 into a pi 0, pi 0. Okay. So we know from the text that JPC of the eta 0 is 0 minus plus. And so we can say a lot of things. The initial orbital angular momentum must be 0, and so also the final angular momentum must be 0, which is L pi pi plus S pi pi, which is just L pi pi, which must be 0 for angular momentum conservation. Then we know that initial charge conjugation value is +1, okay? And so also the final one must be +1 for C conservation in electromagnetic processes. So this is the charge conjugation of the pi zeros. The pi zeros are eigenstate of C with eigenvalue +1, as we have seen. So this is a +1 squared, that is +1. And in fact, it corresponds to the initial. Okay. Let's now check parity. So the parity in the initial state is -1, as we know from the quantum numbers. And so we have to check that parity in the final state is also -1. So this is -1 L pi pi times intrinsic parities. That is -1 to the 0, because the angular momentum is 0. And then we have -1 times -1. So in this case, if you take the value, you get a +1. And this is indeed a problem, because this is different than the initial state parity. Okay. And so, as a consequence, parity would not be conserved in this electromagnetic decay, and so, in fact, this decay is forbidden. And the experimental value of the branching ratio for this decay is indeed smaller than 3.5 10 to the minus 4. So this is an experimental upper limit. Let's consider now the other. So now the eta 0 going into 3 neutral pions. Again, from our JPC equals 0 minus plus, we obtain that the JI is equal to 0, and so the JF, which is L12 plus L3 plus S pi pi, this must be 0 also. Now let's check parity and charge conjugation. CI, it is +1, as we know from the text. Let's check CF. So this is the charge conjugation of the 3 neutral pions. That is +1 to the 3rd power, that is +1. So, okay, it corresponds to the initial state charge conjugation. Let's consider parity. Initial state parity, as we know, is odd. And so the parity of the final state is -1 L12 plus L3 times the intrinsic parities. That is -1 L12 plus L3 times -1 to the cube. That is -1 to 0 plus 1 that is -1. Okay, so this we can write as indeed -1 L12 plus L3 plus 1. And so, yes, in this case, it corresponds to the parity in the initial state. So parity is conserved, charge conjugation is conserved, and in fact, this decay is allowed by the conservation rule. And in fact, the experimental value of the branching ratio in this case is pretty large, is order of 0.326. Okay. Let's now solve the last one. So consider the strong reaction pi minus plus deuteron that goes into neutron plus neutron, where the pi minus is captured by the deuterium nucleus in a p wave. Now, using that the parity of the deuterium is even, so +1, show that the 2 neutrons must be in a singlet spin state. Okay. So this is problem 4.7. So let's consider the reaction, indeed, the pi minus plus deuterium that goes into neutron, okay? And we know from the text that the pi minus is captured by the deuterium in a p wave. And also we know that the parity of the deuterium is +1, okay? So the fact that the pi minus is captured in a p wave, this means that in the initial state, let's say L initial must be 1. So the parity in the initial state is -1 to the L times the intrinsic parity of the pi minus times the intrinsic parity of the deuterium. Okay, so our initial state particles. So since the system is an EP wave, this is -1 to the 1. Then the pi minus is a pseudoscalar, so it comes with a odd parity. And as we know from the text, the parity of the deuterium is even +1. So overall, this is +1. Now, since, as we know from the text, the reaction is regulated by the strong interaction, again, parity must be conserved. So we must have that also the final state parity must be equal to +1. Is there a question?
Yes, sorry, why the L? Because that's just for the deuterium.
No, let me read again the text. So consider the strong reaction pi minus plus D that goes into NN, where the pi minus is captured by the deuterium nucleus in P wave.
Okay, sorry, I misunderstood.
No, okay. So this means that the initial state must be in a P wave. So the initial state angular momentum is 1. Okay. So now, so we have the parity in the initial state. We know that the reaction is strong. So we also expect that the parity in the final state must be the same, so +1. So let's write down now the parity for the final state, PF. This is -1 L of the neutron pair system times the parity of the first neutron times the intrinsic parity of the second neutron. This is -1 L n n. The neutrons are baryons, so they are both come both with positive intrinsic parity by convention, as we have seen yesterday. So this is just -1 L n n, and this must be equal to +1 because we are enforcing a parity conservation. And so as a consequence of this, we know that L and N can only be an even number, so 0, 2, 4, etc. Okay. Now, since the final state particles are two identical fermions, we have to ensure that the total wave function is, in this case, anti-symmetric for exchange of the two identical neutrons. So in general, as you know, the wave function of a system of particles, it can be split into a spatial term and a spin term. Okay, and as we've studied a couple of lessons ago, the symmetry of the total wave function is given by -1 to the L n n for the spatial component and -1 to the S plus 1 for the spin component being a system of fermions. Okay, this we have studied 2 lessons ago. So this is for the first is a spatial. Sorry. And the second is the symmetry of the spin component. Okay, so we have the first must be +1 because L can only be an even number, 0, 2, 4, whatever. Okay, and then for the second we don't know, so this is still -1 S plus 1. Okay, but we know that the total wave function must be anti-symmetric. Okay, because we have a system of two identical fermions. So this must be equal to -1, okay, antisymmetric. And so the only possibility is that S plus 1 is odd, or equivalently that S is even. So we have a system of two spin 1/2 fermions, the two neutrons. Okay, so as you know, they can arrange themselves either in an S equals 0 singlet spin state or in an S equals 1 triplet spin state. Okay, but since S must be equal, then it turns out that the only possibility is that they arrange themselves into a S equals 0 singlet spin state. That is what we were required to show in this problem. Okay. So this was the last problem today. If you have questions, just go ahead. Otherwise, we can make a break and we recombine at 15 past 12.
I think it's okay.
Okay,
No question, thank you.
perfect. So see you in 8 minutes. Ok, ricominciamo. Ok, mi sentite? Vedete le slide?
Sì, prof.
Okay, bene. Okay, so we now completed module 4 about discrete symmetries, and we will now start the module 5, which is a quite long chapter of the course. It is all about hadrons. So today we'll start speaking about isospin, and then we will continue in the next weeks. So some brief recap. So each strongly interacting particle that we call hadron in general is characterized by its mass and by several quantum numbers, which are divided into two categories. So the first category is the so-called space-time quantum numbers, which include angular momentum, parity, charge conjugation, of course, only for those which are eigenstate of C. And these quantum numbers are denoted, as we have seen also today, as JP or JPC. And the other category are the internal quantum numbers. So these are not associated with the motion or the spatial properties of the wave function. And those include the electric charge, Q, baryonic number, B, that we introduced yesterday, and all the flavor quantum numbers, so the isospin that we will discuss today, strangeness, charm, beauty, truth, etc., which reflect the quark content of the hadrons. Now, the internal quantum numbers are additive, in the sense that their values for a given hadron, for instance, for a baryon or a meson, can be obtained by adding those of the valence quarks or antiquarks that constitute the hadron. As we will study next in QCD, valence quarks refer to those quarks that indeed provide the quantum numbers of the hadrons. Then, in addition to the valence quark, as we will study, there is a sea of infinite quarks, antiquarks pairs inside hadrons, which are produced by the gluon splitting. But this will be studied next in QCD. So let me start today with isospin. So the strong force, as you know, is independent of the electric charge. And experimental evidence derives from the equivalence of the proton-proton, neutron-proton, and neutron-neutron interactions once all the Coulomb effects are subtracted or corrected for. And historically, this equivalence was deduced from the remarkable similarity of the energy level of the so-called mirror nuclei, which are nuclei with a neutron replaced by a proton or vice versa. So let me give you some examples here. So here we have 5 nuclei. The first pair and the last pair, those in the red boxes, are indeed the example of mirror nuclei. So this is the nitrogen with oxygen, where indeed one proton is swapped into one neutron, okay, or vice versa. And this is the case of oxygen 17 with fluorine 17. Again, the only difference is that a proton is interchanged with the neutron. Whereas the one in between is oxygen 16 is not a mirror nucleus, so compared to the other. So now, if you now compare the pattern of the energy levels for these nuclei, you see immediately that for the case of mirror nuclei, so either this pair or this pair, the pattern of energy level is extremely similar, okay? Not only in the energy level, but also in the spin and the parity quantum numbers. There are, of course, few differences, okay? They are not exactly the same, and these few differences are only due to electromagnetic effects, okay? Whereas if you take a similar object, which is the oxygen 16, you see that the pattern is completely different. So in other words, if we swap protons and neutrons, the strong interaction, the strong force essentially does not notice it. And in this sense, protons and neutrons can be regarded as two different charge states of a single strongly interacting object that we call the nucleon, and we denote as capital N. So the neutron comes essentially in two charge states, the proton with positive charge and the neutron with neutral charge. So how can we now distinguish the two, okay, concerning the strong force? So let me introduce this new quantum number that we call isospin, and we indicate with I. So the nucleon N is assigned an isospin equal to 1/2. And the protons and neutrons are distinguished by the third component of this isospin, so I3. So the nucleon is an isospin 1/2 object, and these two components, the proton and the neutron, are distinguished by the value of the third component, which is +1/2 for the proton and -1/2 for the neutron. You can also see graphically here, okay? So the total isospin is 1/2 for both of them, but when you project them into third component of isospin, then you have the two possible values, -1/2 for the neutron and +1/2 for the proton. Electric charge is related to the third component. Of course, the two are different due to the electric charge, so there must be a connection between electric charge and third component of isospin, and the connection is given by this simple relation here. So, for instance, for the case of proton, the third component is +1/2. So if you put +1/2 here, you get 1, and in fact, the charge of the proton is +E, where E is the electron charge. For the neutron, instead, we have -1/2. If you put here -1/2, you get 0, which is indeed the charge of the neutron. Now, if a scattering or decay process proceeds through the strong interaction, then both isospin and third component of isospin are conserved. So this holds for all strong processes. If instead it goes through the electromagnetic interaction, then only the third component of isospin is conserved, but the total isospin is not. And if the process is regulated by the weak interaction, then they are both violated, both I and I3. Now, a clear manifestation of the isospin symmetry is the closeness of the proton and the neutron mass. So let me put here the full expression of the mass of the proton and the neutron. You see the two are quite close, and the difference in mass is of the order 1.3 MeV. And this small difference, indeed, arises solely from Coulomb energy term. So by electromagnetic interaction between the pairs of quarks. So what we can say more here? Of course, apart from their charges, protons and neutrons have also slightly different masses, as we have just seen, which arise from electromagnetic effects only. So we can say that the isospin symmetry is not an exact symmetry of nature, okay? It is, let's say, a broken symmetry because the two masses are not exactly the same. However, the mass difference, which is of the order of 1 MeV, is very small compared to the proton or the neutron mass, okay? And furthermore, the electromagnetic interaction, which is responsible for this difference, is 2 orders of magnitude weaker than the strong interaction. So in other words, the isospin symmetry is still a fairly good one. It is only slightly broken. And the level of breaking is just given by the difference of the masses, normalized to the mass of the proton. So so the level of breaking is of the order of 1 per mil, a very small level. So in other words, the isospin symmetry is a very good symmetry, although not exact of nature. Now, as you know, at fundamental level, the strong interaction occurs among quarks. And the valence quark content of the proton and the neutron is the following. So the proton is made by the up, up, down, and the neutron by up, down, down. And so we can now extend our discussion of isospin to the valence quark of protons and neutrons, okay? So to the up and the down quarks. So it turns out that we can also assign E equal 1/2 to both up and down quarks, and distinguish them again by the third component, which is +1/2 for the up quark and -1/2 for the down quark. Again, you can see also here in the graphically, okay? Now, for any state which is composed of quarks and antiquarks, so any hadrons essentially, the value of the third component of isospin is related to the number of quarks and antiquarks by this relation. So it's 1/2 Nu minus Nd, where Nu is the total number of up quark minus the total number of antiquark, and Nd is the total number of d quarks minus the total number of anti-d quarks. Okay? So for the case of the proton, okay, we have 2 up quark and 1 d quark, and then we don't have anti-quark as valence quarks. So for the case of proton, this is just 1/2, 2 minus 1, so it is indeed +1/2, which is indeed the third component of isospin for the proton. For the neutron, instead, we do have 2 down quarks and 1 up quark, and not valence antiquarks. So in this case, it's 1/2, 1 minus 2, and you get the -1/2 for the third component of isospin for the neutron. Now, we've already introduced global transformations of this form here, E to I alpha, where alpha is the parameter of the transformation, depending on a single parameter alpha. And as we have seen, these form a unitary group U1. Okay. Now, the isospin transformation are also unitary global transformation of this form here. So just a little bit more complicated, but the structure is essentially the same. Where U, which encodes this transformation, is a unitary operator. So what we have here, so the theta I are the parameters of the transformation, okay, and the tau I are the generators of the transformation. And this is, of course, general for any kind of transformation that we have been studying. Now, these three generators are conventionally chosen to be the Pauli matrices. So we will call them tau instead of sigma, but they are exactly the three Pauli matrices. Now, in general, the set of all unitary 2x2 matrices form a U2 group. Okay, but the Pauli matrices are somehow special because, in addition, they have the following properties. So the determinant of all of them is equal to 1, and the trace is equal to 0, where the trace means the sum of the element in the principal diagonal. Okay, and so they constitute a subgroup of the U2 group, which is called SU2, which stands for special unitary matrices. Okay, so in other words, the three Pauli matrices form a SU2 group, a group of special unitary matrices. And we say that isospin transformation form an SU2 group, and that isospin symmetry arises from the invariance of the Lagrangian of strong interaction under SU2 isospin global transformations. Okay.
Prof?
Sì.
Question.
Sure.
When we introduce the group transformation SU2 and in the 3D space, we can do this basically because there is a homomorphism between SU2 and SU3. But in the fourth dimension, I mean in the Lorentz space, why we can do why we can use SU2 in the Lorentz space? Because the group of the Lorentz transformation are I mean ortochrone in Italian, I mean SO3, 1. Magari non sono stato molto chiaro, non so se accolgo.
Però in italiano.
Cioè, nel senso, noi abbiamo introdotto SO2, siamo tranquilli di usarla nello spazio 3D perché c'è un omomorfismo tra SO2 e SO3. Però nello spazio a 4 coordinate, che è quello di Lorentz, io a livello teorico non sono sicuro di poterlo fare. Domando, lo possiamo fare perché il gruppo delle trasformazioni di Lorentz è un gruppo ortocrono ed è parametrizzato da SO3,1, dove il tempo viene lasciato a parte. Questa era la domanda.
Ok, allora non credo di saperti rispondere, nel senso che, in English, I'm not an expert of group theory. I think we are talking about different things. Okay, so what we are talking here, we are just restricting ourselves to this kind of global accidental symmetry of the QCD Lagrangian, which is the isospin symmetry. And since this is determined by 3 generators, this can only be an SU2 group. So I think the two things are not in contradiction, but we are talking about different things.
Ok, grazie intanto.
Okay. So, okay. Now, few general remarks about the SU2 or SUM in general. So SU2 matrices are of the form, this one, AB minus B star S star, which is a complex conjugate, where A and B are complex numbers in general, such that indeed the sum of the square modulo is 1, which corresponds to essentially the determinant being equal to 1. The dimension of the special unitarity group in general, SUN, is n squared minus 1. Therefore, the dimension of SU2 must be 3, because it is 2 to the square minus 1, which is 3. And so, in fact, SU2 transformation depend on 3 global parameters, the theta I, and the 3 generators, which are the 3 Pauli matrices. Similarly, one can go ahead, so one can consider SU3. In this case, we have 3 to the second minus 1, so you have 8 parameters and 8 generators, and this will be the case for the QCD, for instance, or for the flavor symmetry, as we will study next, etc. And this you can generalize for any dimension. Now, more precisely, the Pauli matrices are said to constitute the fundamental representation of SU2. And the basis of this representation is conventionally chosen to be the eigenvectors of the tau3, so the third Pauli matrices, okay, which are simultaneous eigenstate of I3 and I squared. So yeah, so let me put this in a moment on the board. So we can choose this basis to describe the up and down, or equivalently the proton and the neutron isospin states. Okay, so the isospin state of the up quark or the proton will be 1, 0, and the isospin state of the down quark of the neutron will be 0, 1, where indeed 1, 0, and 0, 1 are the eigenstate of the tau3 Pauli matrices. And let me just very quickly show these on the board. Okay. So as we said, the convention is that the isospin eigenstate for the up quark or for the proton is 1, 0, and that for the down quark is 0, 1. So let's now try to work out the eigenvalue equation of the third Pauli matrices. So this is 1, 0, 0, minus 1 acting on our eigenstate 1, 0. If you do now the matrix vector product, you just get 1, 0 trivially. So this is plus 1 u. Let's now apply this to the down quark isospin state. That is 1, 0, 0, minus 1, now acting on 0, 1. Now, in this case, you get 0, minus 1. That is minus 0, 1. That is minus 1 d. Okay, so in other words, 1, 0 is eigenstate of tau3 with eigenvalue plus 1, and 0, 1 is eigenstate of tau3 with eigenvalues minus 1. Now, let's go back to the slide. And this is indeed what we just shown on the board. Okay. Now, if you pay attention, this is exactly the same notation which is used for spin up and spin down state for a spin 1/2 particle. Okay, it's just exactly the same notation, the same formalism. Okay, and we can make these even more transparent. So instead of using tau I as the generators, we can multiply by 1/2, and in this way we define the 3 components of this isospin vector: I1, I2, I3, which are of course trivially given in terms of the Pauli matrices. And so our transformation now becomes in this way. Okay, where we now have I instead of tau I divided by 2. And these 3 components, I1, I2, I3, just act exactly the same way as the 3 components of the angular momentum. We said that they have exactly the same Lie algebra, in the sense that they have exactly the same commutation rules. So for the angular momentum, you know from quantum mechanics that they commute in this way, the three components, and this is exactly the same algebra, the same commutation algebra that we have for the case of the isospin, okay? Where epsilon jkl is the standard Levi-Civita tensor, which is +1 for cyclic permutations and -1 for anticyclic permutation. And you see some example here. Now, in the language of group theory, I equal 1/2 particles, such as the proton and the neutron, or equivalently, the up and the down quarks, they constitute isospin doublets, okay? And in general, an isospin multiplet contains 2 I + 1 members, okay? So if I is 1/2, as for the case of the nucleon or the up and down quarks, then you just get 2 members, which have to have similar masses, okay? Ideally, equal masses. And now, since isospin has the same algebra of spin, okay, the isospin state of a system of 2 light quarks can be written in complete analogy with a combination of 2 spin 1/2 states. So also in this case, we can have a singlet state, okay, where now we use the up and down notation instead of the up and down arrow. This is for spin, this is for isospin, but you see, everything is the same. And the other possibility is a trivet state, okay? Again, I didn't put the comparison, but you understand that by changing the up with the up arrow and the down quark with the down arrow, you get exactly the same notation. So the first state is an I = 0 isospin singlet, which is also in this case antisymmetric under exchange of up and down quarks. Whereas the other 3 states form an I = 1 isospin triplet, which is indeed instead symmetric under up and down exchange. And this you can see immediately here, okay? Now, in the language of group theory, we say that 2 isospin doublets decompose into an isospin singlet here and an isospin triplet there. Okay, so symbolically, we write these in the language of group theory. So we start from 2 isospin doublets and we end up with an isospin singlet and an isospin triplet. And as you can see it graphically here. So the singlet has E = 0, and so also the third component is 0, and this is our antisymmetric state, this guy here. And for the triplet, we have the 3 possible projections, 0, +1, -1, and this is the decomposition in terms of up and down quarks.
Professor?
Yes.
I have a question. I didn't catch why the isospin only considers the 2 light quarks, so not the other flavors. Why is it?
Indeed. This will be clear from the next lesson.
Okay.
So the isospin was introduced much earlier than the discovery of the strange quarks or the C quarks, etc. Okay, so it was already in the time of nuclear physics, and as I mentioned before, this was indeed discovered by comparing the energy level of mirror nuclei. At that time, there was no clue for the strange quark and for the other heavier quarks. These have been proposed later in time, as we will study next. And indeed, so you catch the point, because the isospin is essentially the name we indicate the flavor for the up and down. And it is essentially equivalent to the strangeness for the strange quark, the charm for the charm quark, etc. Okay. So adding all the other is just an extension of this formalism. And this will be clear in the next lessons.
Okay, thank you.
Thanks for raising this point. So what about baryons? So baryons, as you know, are bound state of 3 quarks. So in this case, we have 3 iso doublets, and based on group theory, okay, they decompose into a isospin 3/2 quadruplet and 2 isospin 1/2 doublets. And this is the result. So the quadruplet has an I 3/2, so it comes with 4 projections: -3/2, -1/2, +1/2, +3/2. And you see here the corresponding wave function in terms of up and d quark. And the 2 doublets, which have both I = 1/2, okay, but have different combination of up and down quarks. So it is now important to check the symmetry of these multiplets, okay? So for the quadruplet, okay, so 3/2, and then we have the 4 projections. These states here are all symmetric under exchange of any 2 quarks. So S stands for symmetric, fully symmetric. And this you can immediately check by eye. Whereas if you now look at the 2 doublets, okay, these 2 guys have a so-called mixed symmetry or mixed asymmetry. What does it mean? Mixed symmetry means that they are only symmetric under the exchange of the first and the second quark, and mixed asymmetry means that they are anti-symmetric only under the exchange of the first and the second quark. And so mixed symmetry and mixed asymmetry states have no definite symmetry under the exchange of the other combinations, so 1 to 3 and 2 to 3, but only for 1 to 2, only for 1 to 2. This will become relevant when we will build up the wave function of the proton later on in the course. What about now antiquark? Of course, we can define isospin also for the antiquarks, and the convention for the antiquark isospin doublet is the following. So to have on top minus d bar and on bottom u bar. And this choice with the minus sign here might seem quite strange, but it is required in order to have exactly the same transformation rules for quarks and for antiquarks. And so, and such that the physical predictions are invariant under simultaneous exchange of up into down or anti-up into anti-down. So formally, you need to have this minus sign here in order to get these equivalents. And the general rule for both particle and antiparticle is that the most positively charged particle has the highest value of third component of isospin. So in the case of quark, of course, the charge of the up quark is plus 2/3, okay? So it comes with the highest value, plus 1/2, whereas the charge of the down quark is minus 1/3, and so it gets the negative projection. For the anti-quark, of course, also the charge is inverted, okay? So the charge of the anti-down is now plus 1/3, that is higher, in a sense, more positive, than the charge of the anti-u bar, which is minus 2/3. So in this case, it is the minus d bar, or the d bar if you like, that gets the higher value of the isospin projection, and the u bar that gets the lower value. And this is a general rule. Now, we discussed about baryons. What about mesons? So mesons are bound state of a quark and an antiquark, as you know, okay? And the 4 possible isospin states of light mesons are obtained from the combination of what? Of an SU2 quark doublet and an SU2 antiquark doublet, isospin doublet, okay? And one then obtain, again, a triplet and a singlet state, but now with a different combination, because now we are merging quarks and antiquarks. So it turns out that, in this case, the singlet state is symmetric under exchange of d versus u and d bar versus u bar, as you can see here, okay? Whereas the 3 triplet states are, in this case, anti-symmetric under the simultaneous exchange of d versus u and d bar versus u bar. Okay, so the symmetry is opposite to that one that we have seen for a system of up and down quarks. Now we are decomposing a quark doublet with an anti-quark doublet, and so in group theory you obtain these again in a singlet, which we can visualize here, which is symmetric, and the triplet, which is here with the 3 components of the isospin -1, 0, and +1. As we shall see already today, the triplet state corresponds to the 3 pions, whereas the singlet state turns out to be a mixture of the eta and eta pi mesons, and this will be studied ahead of the course. So let me now open a parenthesis on the discovery of pions and on the measure of their the spin. And let me go back indeed to the Yukawa idea, okay, that we already discussed, but let me just take this again once more. So the pi zero, or sorry, the pi meson, or just pion, was, as you know, predicted by Yukawa already back in 1935 to be the mediator of the nuclear force, where nuclear force is the one that keeps the nucleus bound together against Coulomb repulsion among the protons. And the nuclear interaction was described by the Yukawa potential that we already discussed and studied quite in some detail, okay? Where R gives you the range of the nuclear interaction. Now, given the experimental evidence at the time that the range of the nuclear forces is of the order of 1 Fermi, so essentially the size of the proton, Yukawa predicted that the mass of the expanded meson, through this relation here, must be of the order of 100 MeV. So the following year, so in 1936, a penetrating charged particle with a mass of the order of 100 MeV was discovered in the atmospheric showers generated by cosmic rays. And of course, it was immediately associated with the Yukawa meson. But it was a big mistake. Because in 1947, so more than 10 years later, a famous experiment performed by Conversi, Pancini, and Piccioni demonstrated that this particle, so the one discovered in 1936, is not absorbed when passing through a layer of material. But if it were the Yukawa particle, it should have interacted so strongly with the nuclei in the material to be immediately absorbed, so absorbed before decaying. And so, indeed, it turned out that the particle discovered in 1936 could not be the pion, could not be the Yukawa particle, but something different. And it was then understood that it was instead, let's say, a heavier brother of the electron that we call the muon, okay, with a mass roughly 200 times higher than that of the electron. So nothing to do with the pion. The pion was instead discovered, or mainly observed in 1947 by Occhialini and Powell, still looking at cosmic rays showers, by exposing emulsion stacks at an altitude of 5,500 meters in the Andes mountains. So why people had to go uphill in the Andes? Because at that time, this was just after the Second World War, there were no high energy accelerators in physics laboratories. So the only way to look at high energy physics was to look at cosmic rays. So what they observed a new particle this time with a mass still of the order of 100 MeV, but now decaying in exactly the penetrating particle that was observed in 1936. So this new particle was indeed decaying in M1. Furthermore, it was also observed that the energy of the muon was always the same, and this was indicating clearly a two-body decay into M1, which was observed, plus something that was not observed. So there had to be some neutral undetected particle, which is later recognized to be the muon neutrino. Okay. And in 1949, the complete decay chain was captured in a high sensitivity emulsion in one of these cosmic rays experiments. So people was able to detect the track of the incoming pion. Okay. Then at a certain point, the pion was decaying into the muon, and then further the muon was further decaying into the electron. Today we know that, of course, these decay are regulated by the weak interactions. So the full expression of the decay have to take into account also the corresponding neutrinos, the way they are reported here. Okay, and this will be studied, of course, in the weak interaction chapter. Now, since according to Yukawa theory, the pion should mediate the proton-proton, but also the proton-neutron and also the neutron-neutron interaction, it was understood that it should exist in 3 different charges, in 3 different charge states, the pi plus, the pi 0, and the pi minus. And the final proof of the observation of the pions was indeed through nuclear reactions, okay? So with the observation of this absorption reaction, where the pion is absorbed into a nucleus, okay, either a pi plus or a pi minus, transforming a proton into a neutron or vice versa, okay? So in this case, you are transforming a neutron into one proton, in this case, one proton into a neutron, okay? So this was indeed the final proof that indeed the pion regulates the nuclear interaction, and so the interaction between protons and neutrons, essentially. Of course, today, we know that at fundamental level, the nuclear force is only a residual force of the more fundamental strong force, which occurs at fundamental level between quarks, and it is mediated by gluons, okay, which are the gauge bosons of the strong interaction, as we will study next in QCD. Now, the properties of pions could be now finally systematically studied with the advent of the first particle accelerators. And the first accelerator with sufficient energy to produce pions was this very large cyclotron at the Berkeley University, which could accelerate alpha particle up to 380 MeV. So with this beautiful machine, they were able to make interesting studies and to characterize, indeed, for the first time, the pions. So the mass of the charged pions was measured through the relativistic relation. The mass is just the inversion of the energy momentum relativistic relation, through the simultaneous measurement of the energy and the momentum. So the momentum was measured through the radius of curvature of the tracks inside a known magnetic field. As you know, when a charged track crosses a magnetic field, it bends. So one can measure with the tracking detector the radius of curvature. And by knowing the intensity of the magnetic field in Tesla, you just get, by this simple relation, the value of the momentum in Jeff/c. And the energy, which is the second ingredient, instead was measured by measuring the range inside the emulsion bricks, the range before stopping inside the material. Okay, and so overall, they found these results. So 131 MeV for the pi plus, and essentially the same value for the pi minus. Okay, which are of course absolutely consistent within the large uncertainty that they had at that time. Now we can compare these results with the present values of the pions, okay, which is here reported. Okay, of course the precision is immensely increased over time, and you see that the mass of the pi plus and the pi minus is indeed exactly equal. This is, if you like, also a consequence of the CPT theorem that we discussed yesterday. And the mass of the pi zero is slightly lighter, only a few MeV lighter, so it's order 135 MeV compared with 140 MeV, okay? And the lifetime of charged pions could only be measured after the advent of fast detectors and fast electronics, okay, with a resolution at least of order of several nanoseconds. And the present values for the lifetime are 2.6 10 to minus 8 seconds for the charged pions, which is a quite long time, so it is typical of weak decays, and 8.4 10 to the minus 17 seconds, which is now a much faster process, which is typical of electromagnetic processes. Okay, and in fact, we know that while charged pions decay weakly and lose relatively slowly, neutral pions decay electromagnetically, so essentially through the production of a photon pair, and lose much faster. Now, what about the spin of pions? The spin of pions was measured through the ratio of cross-section for the forward and backward reaction, so by exploiting the principle of detailed balance that we studied yesterday with the time reversal operator, if you remember. Okay, so we have in fact now two reactions, which are one the time reversal of the other, pi plus into d that goes into proton pair, or proton-proton that goes into pi plus d. So the reaction in the numerator, which is an absorption reaction where the pi plus is absorbed by the deuteron, this was measured in 1951 using a pion beam of 24 MeV, and the production cross-section in the denominator, where now the pion is produced, this was measured 2 years later using a proton beam of kinetic energy 341 MeV, but the center of mass energy of the two are almost equal. So now we can write down the full expression of the cross-section, essentially the way we derived starting from the Fermi-Golden rule, as you remember. But in the ratio, most of the terms cancel, including also the S Mandelstam, which is the center of mass energy, which is indeed almost equal for the two reactions. And what only remains in the ratio is the spin multiplicity for the proton, the pion, and the deuteron, and the ratio of the momenta of the final state particles. So for the spin, it was known already at the time that the proton had a spin 1/2 and that the deuteron had a spin 1. So the only unknown was the spin of the pion. So at the end, you end up with this simple relation. And then the momenta of the final state proton and final state pion, these were measured in the way I mentioned before. Okay. So the only unknown for these was indeed the spin of the pion. And so by inverting this relation, by measuring the cross-section of the two reactions, it results that the quantity 2s pi plus 1 must be equal to 1 within uncertainty. And so the only possibility is that the spin of the pions is 0. Okay? So this we assumed already in the past lesson, so by saying that pions are scalar, actually pseudo-scalar, but this is the way it was measured. And as we have seen, the masses of the 3 pions are very close, okay? The charge of the neutral pion masses differ only by a few MeV, and this small mass difference is only due to electromagnetic contribution. Okay, so it is not a surprise that the 3 pions form an isospin triplet. Okay, so the 3 pions minus UD bar, UU bar minus DD bar, and DU bar form an isospin triplet with I equal 1, and they are corresponding to the 3 projection, +1 for the pi plus, 0 for the pi 0, and -1 for the pi minus. And that's it for today. Questions, comments? Okay, if not, we will continue next week with the isospin, and we will see how to get prediction on the cross-section by enforcing isospin conservation in strong reactions. And then we will extend our discussion, including strangeness and so on. Ok, se non ci sono domande, allora vediamo settimana prossima. Vi auguro un buon weekend.
Grazie mille, anche lei.
Arrivederci, anche a lei.
Arrivederci. Vi metterò poi i testi dei problemi sulla classe, visto che non ci sono più.
Ok, thank you.
Okay,
Arrivederci.
Ok, arrivederci ragazzi.